Oh, hello, everybody. So the big issue I had today was my microphone on my computer decided it wasn't going to record. So I apologize for that because you missed out on some of these slides. So I'm going to ask you just to be sure that you look through them on your own so you can still get the same material. But this slide and the next couple slides, there's some big ones I want to talk about to make sure that you guys get the same information that everyone else does. So if we look here, the Hardy-Weinberg principle is the idea that we can predict what the phenotype and the genotype of a population are going to be if we follow a few rules here. So the Hardy-Weinberg principle says if no evolution is occurring in a population, genotype frequencies can be predicted by math. This is one of only two math equations that I will teach you in ecology this year, and that's fine with me because I don't want to have to teach you a lot of math because otherwise you'd be in a math class. Some rules that are important to remember. There can be no random mating. No mutations can occur in our population. We have to have a large population size, so about 1,000 individuals or so, and we can't have any immigration occurring in and out of our population. And all those individuals in our population must have an equal fitness for this to occur. So the big question here that we need to think about is, can this actually occur in ecology? And the answer is no, it's not going to occur in nature because we're not going to have individuals randomly mating. We're not going to have a population where there are no mutations occurring because each individual by themselves either has a small mutation of some level. We have to have a large population size, which is possible. We have no immigration at all. And the last one, which I will see here in a second once that bar disappears, equal fitness. That's just not true in a population. So the only place that we actually see this type of situation occur is on agricultural facilities such as farms, dog breeding, situations where people are driving this. So we can never actually use this successfully in nature, but we can use this to make predictions about human-driven populations. So if we go to this next slide here, there are two equations that work with the Hardy-Weinberg. There is the P plus Q equals 1, and then there is P squared plus 2PQ plus Q squared equals 1. And I know this looks a little bit intimidating, but this is actually a really easy equation. P squared literally just stands for the percentage of homozygous dominant individuals in our population. 2PQ represents all our heterozygous individuals in the percentage of heterozygous individuals in our population. So that would include any individual that has both dominant and recessive alleles in their genotype. And then the last one, Q squared, means homozygous recessive in our population. That's the percentage of individuals that are recessive for our genotype. So we can use this with a select population that follow those 5 rules that we just talked about in the previous slide to make some predictions about the types of genotype and phenotype we will see in these populations. So if we look here, we have an example. We have 8% of the Somerset chocolate lab population has blue eyes. And we look up here in these top right, we look at these beautiful blue eyes that these chocolate labs have. Blue eyes is recessive, meaning they have lowercase b, lowercase b. So we want to find out what percentage of individuals in the population does not have blue eyes. So we need to find out what our frequency of dominant allele traits occur in our population. We can use that using the two equations we saw before. We want what is the frequency of the dominant B and the recessive B allele? So that's just going to build on question 1. And then 3, what percentage of individuals in our population are heterozygous, meaning that they have a dominant B and a recessive B in their genes. So if we go to the next slide here, we can work out this math. So we have, again, 8% of the Somerset Chocolate Lab population has blue eyes. So if I go to, all right, so sorry about that. I had to make another clip. I'm still trying to figure this screencastify stuff out that I use. So if I come back down here and I grab my pen, we had the equation up there, P plus Q equals 1, and then we had P squared. And I'm, again, sorry that this isn't working. And it's also going to be huge. Plus Q squared. So those are our two equations that we're going to use for Hardy-Weinberg. So we have 8%. So we're going to go 8. And that is equal to our Q squared. So then what we want to do, and I'm sorry, but that does says 0.08 equals Q squared. And what we want to do is we need to figure out how many individuals in our population possess a dominant allele. So what we need to do is we need to convert this to Q. So we're going to take Q, and we're going to take the square root of 0.08, and that's going to give us our Q value. So if we plug that into our calculator, square root of 0.08, and we press equals, we're going to find out that that equals to 0.28. And that is the total number of individuals that contain a recessive allele in our population. So 28% of all of our entire population contain individuals that have a recessive allele. So to figure out how many individuals in our population, or what percentage of individuals in our population contain a dominant allele, what we're going to do is we're going to take 0.28, subtract it from 1. So if we take our first equation 1, we subtract 0.28. That's going to be equal to our p-value. So that's you can use your calculator if you want, but that's pretty much mental math. So 0.28, 1 minus 0.28 is going to be 0.7, and that's huge and disgusting, so I'm sorry, 0.72. So 72% of all of our individuals in our population have a dominant allele in our population. So that answers question 1. So for question 2, we want to figure out, well, what percentage of our population has either the frequency of recessive traits in our population, and what percentage of our population has a dominant trait. And we've already done that, actually. So I'm going to go ahead and highlight this in blue. These are our allele frequencies in our population, showing that us at 0.7 or 72% of all individuals have a dominant allele, and 28% of our individuals in our population have a recessive allele. For the last question, so number 3, what we're going to do, and I'll do this in a different color. Let's do it in black. So in our last one, actually, I wonder if this will work best. So on our last one, if we take, we have to figure out what the 2PQ is. So this works really good. 2PQ is equal to 1. That will tell us what percentage of our individuals in our population are heterozygous for eye color. So we can just do 2PQ equals 1, because we know right here, we already found it, what P and Q are equal to. So if I take 2 times 0.28, number of percentage of individuals that have a recessive allele, and 0.72, number of individuals that have a dominant allele, and we multiply those things together. So we take 2 times 0.28 times 0.72, and that's going to be 0.40. I'll move this up a little bit so that I can write. So I'll move this up in the corner so I can write. So 0.40, that is the percentage of individuals that, yeah, you do. That is the percentage of individuals that have heterozygous genotype, meaning they have a dominant and a recessive. So if you have any questions about that, please let me know. This next slide here, so I'm going to exit that, move this guy back over into this corner. The next slide here, if I go forward, if it will let me go forward, I have to pause this for a second so it lets me go forward. Well, for some reason, it won't let me go to the next slide, and that's okay. So on the next slide, there is a practice question that I would like you to do on your own for Wednesday. So come in on Wednesday with that practice question completed. If you have any more questions, please send me an email or come find me. The big thing is that you at least give this a shot. There will probably be one question on our test in a couple weeks about this. I'm not going to make you memorize this or have this down because we can't use this out in nature successfully, but it's a good equation to know. And then there are a couple slides at the end. We will talk about those on Wednesday. So don't worry about those. Just worry about that practice problem, all right? If you have any questions, again, let me know. Hip, hip, cheerio, ta-ta, peace out.